Okay, thank you. So my title is maybe a bit cryptic. So I try to explain this way. I studied the continuity of space translation in non-parametric exponential family based on the exponential Orley space with Gaussian reference density, so that the explanation is worth the title. So the point is simply that in traditional information geometry, there is no description of the state space, because the geometry is on the state of parameters, and there is no relation with the geometry of the state space. And for example, if we take the Gaussian standard density, I call the Gaussian standard density M because of Maxwell, and I consider a density with respect to M of the exponential form, exponential ux minus normalizing constant kappa. And I would like to work with space derivatives of this object. And so as a space derivative is the limit of the increments, first I need to study the translation model. That's the explanation of the title. And I use a setup that I already described in the first GSI conference, and also the paper with joint paper with Lodz was the first example where we tried to study information geometry applied to mathematical physics equation, for example, Boltzmann equation. So the setup is the following. I take a Gaussian, finite dimensional Gaussian probability in space, and all positive densities in this space do have exponential form, just because they are positive. So I parametrize these positive densities with a random variable u in the exponent, exponential u minus a normalizing constant, and u is chosen to have is defined only up to a constant by the density itself, and I choose to have it centered at the Gaussian distribution. Now the random variable u must be such that the exponent is integrable, and that gives the exponential Orley space. So the exponential Orley space in a simple definition consists in simply to admitting that exponential of alpha u and exponential minus alpha u is integrable, and if you collect exponential plus and exponential minus in a cosine, in hyperbolic cosine, you get a special convex function defining the space. And in particular, the norm in this space is less than 1 if the hyperbolic cosine minus 1 of u is smaller or equal 1. So, sorry, the alpha should be 1 here. So there is a nice duality between this exponential space and what one could call the mixture Orley space based on the convex conjugate of the original function. And the two spaces are in separating duality. And the second space is actually related, the space on the hyperbolic cosine minus 1 conjugate is actually of a special type, and there is a domination inequality of the function of alpha y with respect to the function of y. So this is a very classical, setup, and with Carlos Sempe we introduced that a long time ago, and there is a critical presentation in a section of the new book already mentioned by I, Jost, Le, and Schwarzhofer, Information Geometry, just out in these days. And I'm very grateful because they are so nice to devote an entire section to explain why I am wrong in my theory. So there are a number of inclusions. For example, the space L infinity is injected in the space, in the exponential space, and so on. And because of the special reference measure, we can also take restrictions. And we have the restriction you see in the paper. And the case with Gaussian density is also special, in the sense that we can say that all second-order polynomial and all C2 function whose essence is dominated by a constant belongs to exponential space. And the mixture space contains all random variables which are bounded by a polynomial. And actually, this space contains all densities whose relative entropy is finite. So it's related with entropy, the other space. One is related to the exponential family, and the second one is related to the entropy. So in writing down the exponential family in general exponential family in this form, we define a cumulant function or a moment function, and both are convex. They have a common proper domain such that the unit ball is in the proper domain, so the interior is non-empty, and both functions are Frechet differentiable on this open set. Now, there is an interesting feature of this exponential space, and is the fact that the bounded convergence doesn't hold. For example, take fx equal x squared in dimension 1, I consider the approximated sequence of truncation. And then obviously the sequence of truncation converges pointwise to the function and is bounded by a function in the space, but it is not true that there is norm convergence. This is not true, because norm convergence would require that this quantity goes to 0 for all epsilon, and this quantity is plus infinity if epsilon is smaller than 2, so there is no convergence. So nevertheless, this special type of convergence, point-one convergence, and by a bounded sequence, is nevertheless possibly useful. In the following sense, consider an exponential family, a one-dimensional exponential family. Assume we have a sequence of very regular functions, C infinity with Convat support, and the bound in the exponential space such that there is pointwise convergence by a sequence of regular functions which are bounded. So in this way, you can define an approximating exponential family, an approximating one-dimensional exponential family based on the approximation of the exponent, and there is convergence for small t. So there is a small t convergence of this approximated exponential family for smaller value of t. And so that the approximated density is point-wide convergence. By Sheffer lemma, it's a convergence also in L1. And we can do, for example, this computation. Take the derivative of a function in C infinity compact support, have the convergence to the value in the limit density for t small, and then we can compute the derivative and have a sort of calculus of approximation of derivatives. That's an example of what one can do. However, given the fact that there is this lack of convergence, of non-convergence, in Orlich space it is usual to define a smaller class of random variable. Precisely is a closure. In this case, I take the closure of C infinity compact support in the space, in the exponential space. And there is a nice easy condition to say when a function is such in this class, and precisely the condition is that in fact the moment generating function is defined for all values of t. Now, in this setup, I can discuss translation. I take a function, I make the translation, and I can prove that the translation acts on the exponential space continuously. But to get continuity, I need to assume that the function belongs to the Orlich class. It belongs to this smaller class. Closure with respect to the... And then I can compute, similarly, I can compute translation by a probability in a similar way. And the result is that I can construct modifiers and use this approximation technique from functional analysis applied to densities in this class. So that more or less the content of the paper in the proceedings, but I want to add, as suggested by the referees, I want to add some consequences of this setup. One consequence of this setup is that I can prove a sort of Poincaré inequality. The Gaussian Poincaré inequality in the one-dimensional case says that deviation of a random variable from its mean, square integrated, is bounded by the square norm of the derivative, which is very useful because saying, for example, that, well, this says an obvious thing, that a function with zero derivative is constant. In my particular setting, I can prove that there exists a universal constant such that if f is C1 with polynomial growth, C1p, and I take the difference between f and the mean value with respect to the Gaussian distribution, norm in the mixture space, this is bounded is dominated by the norm of the gradient in the same space. For example, if f is a density, the inequality becomes a norm of f minus 1 dominated by the gradient. Now, note that the norm the mixture space is actually related with the entropy. So this is a sort of inequality with for the entropy. And another example, if I take the difference of two random variables which are both m-centered, then u1 minus u2 and expected value 0, and I have this again I have this equality. So I have a bound of the distance in the mixture space between the two random variables based on the norm of the gradient of the difference. So actually, this norm is dominated by the L2 norm. So this actually is a domination with respect to the L2 norm of the gradient of U1 minus U2. And U1 and if U1 and U2 are the score of some statistical model, this quantity is what is usually called the invariant divergence in some application. So we can define differentiable densities, precisely Sobolev space of differentiable densities in the obvious way, and do computation of Machiavellian calculus type. So this setup is actually, because of the presence of the Gaussian density, is actually a part of the Machiavellian calculus, in fact. Because of the functional properties, we have a number of embeddings, Sobolev embeddings between this space. I don't repeat everything. One conclusion is example, if we take a function and derivative in the exponential space, then the function is order continuous of all orders, which is interesting. We can define a directional derivative, and we can define exponential family modeled on this space with derivatives without much harm. We can compute, as I said already, give a precise meaning of to the invariant divergence between f and g, compute it with respect to the score, and it is also possible to compute the natural gradient of the invariant divergence. So it is possible to devise a system to minimize invariant divergence on this sort of models. And finally, also, this is a setup where you can describe what is an elliptic operator, and this is related with ongoing work with Damiano Brigo. And thank you.
Thank you very much for your talk. Are there any questions?
Could you just the first part of the talk was talking about the continuity of translation, and then I didn't immediately see the connection to it. I'm sure it's clear, but
studying the continuity of translations is the first step for studying the directional derivative. And the exponential class conditions ensure the continuity of translation, and now you have to add something to get the differentiability. And this something is a corresponding Sobolev space. At this stage, differentials are available. Differentials are available in this particular space, and then it is possible to start doing mathematical analysis on this object, in particular Malia-Venn calculus.
Are there further questions? Okay, if not, then thank you again.